So this whole thing is now less than or equal to the absolute value of x, which I can rewrite as 4 square root of x squared, but that is less than or equal to the square root of x squared plus y squared. And that's, so I've done what I set out to do and described it over there, came up with a bound for the difference in y's in terms of difference in x's. In more general terms, I've shown that this distance is bounded by this distance. Now, it's not always going to turn out like this. You may instead get a function of this distance. You want to relate these two somehow. In this case, it turned out to be a simple relationship. This distance is less than or equal to this one. So what that allows me to do is that for whatever epsilon I have, I can choose delta equal to epsilon. Then, if this is the case, then the difference between my function and the limit that I think it is, 0, which I already know is less than or equal to this, because that's what I showed over here, which we're already assuming is less than delta, but I set delta equal to epsilon. So, to summarize, I found a delta so that whatever x and y are within delta of 0, 0, function value is within epsilon of 0, therefore, the limit of this function is equal to 0. So once you have an idea of what the limit could possibly be, then what you want to do is find an upper bound for this that relates it to the difference in x values. So the magnitude of x minus a. So in general, if what you find is that the distance between y's is bounded by some function of the distance in x's. So if you have a more complicated relationship between them than what we had here, and g is a function of one variable because its magnitude is just a number. So g has to have be a function that has an inverse, and it has to be an increasing function. Then what will always work, guaranteed, you can choose delta to be equal to g inverse of epsilon. So for example, if you find that this distance between y values is less than or equal to 2 times this distance, g of z would be 2z, then you can pick delta to be equal to epsilon over 2, the inverse relationship, and that will work. Now there are certain properties that apply to limits from single variable calculus. So suppose you have two functions f and g that take in n variables, output m variables, and let's suppose that b, b1, b2 are vectors with m variables, and c is just some real number. Then some things you can say about limits is that limit as x approaches a, f plus g of x. So the limit of a sum is equal to the sum of limits. That rule applies in a single variable and multivariable case. Also, if you take a constant times a function, then what that does is that takes the limit of the original function and multiplies the limit by that constant. So these two properties, another way of putting it is that limits satisfy linearity. They add together, multiply by constants, and everything works as expected, just like with derivatives and integrals. So you can use these two together to figure out that the limit of a difference of functions, f minus g, would be equal to the difference of the limits. So that property is a consequence of these two. Other things that hold, suppose that n is equal to 1, so you only have one output. So f is scalar value. Then you can say that the limit of a product is equal to the product of the limits. So all those natural combinations of limits, adding, subtracting, multiplying, dividing, we look at 1 over f of x, assuming that this is non-zero, you can take 1 over the limit, as long as there's no division by 0 issue to worry about. If you have vector-valued functions, then a vector-valued function is going to have component functions. So what that means is, if the vector-valued function has a limit, then each component function must approach a corresponding component of this vector. Right? So limit exists for the entire vector if and only if the limit exists for each of the components. So they all have to go to that limit together. The continuity, I stated this earlier, means that the limit of a function as you approach a point is equal to function value at that point. So if you have two functions, f and g, that are continuous at a point A, then so are the following: a constant times f, f plus g, f minus g, f times g. If they're vectors, dot product actually works. Division, if f is a scalar, also continuous at that point. No division, but 0 issue. Or if you raise to a power, all those combinations of functions are also continuous at that point if the original function is. Single variable or multivariable, it doesn't matter. There are no surprises there. Because of that, there are certain kinds of functions that we can make some sweeping statements about their continuity. We did it in the single variable case, we can do it again here. So in the 1D case, you often dealt with polynomials. You would have powers of x multiplied by constants, and you would just add them all up. And these are continuous everywhere on the entire real number line. You also had the rational functions, where a function would be a quotient of polynomials. So these are continuous everywhere that f is defined. So as long as the denominator is non-zero, this rational function is defined everywhere else, so it's actually continuous everywhere else. There are also algebraic functions. Example, square root of x, for instance. So 1 over square root of x squared plus 1. Anything like that involving radicals, or something like that. Basically, algebraic functions satisfy a polynomial equation where the coefficients are themselves polynomials. These are also continuous wherever they're defined. So as long as you don't have a division by 0, as long as you're not in a situation where you're taking the square root of a negative number, it's defined, then it's also continuous. Also, trigonometric functions, exponential, logarithmic, all different functions you've seen all follow that same rule, that wherever they're defined, they're at least continuous. Now, all of this applies in the multivariable case. So for instance, polynomial, multiple variables, say f of xy could be something like x squared y plus xy squared plus y cubed. So each term is going to have x and y both raised to various powers. Maybe you would have some constants in here as well. So this is a polynomial in 2 variables, continuous everywhere. Whereas an algebraic function in 2 variables is one we just looked at, xy over square root of x squared plus y squared. This is continuous except at 0, 0 where it fails to be defined. This is on page 3 of the notes. There's an alternative method of defining limits that involves a concept called a neighborhood. A neighborhood is a more general version of what you think of in 1D as a open interval. So once you get to multivariable, there's a more general concept of what's called an open set. So this definition of limits, it might be easier to intuitively understand than a delta epsilon definition, but I'm not spending time on it here because it's not so easy to work with for proving that a function has a limit at a point. In that case, you really want to use the delta epsilon definition. Let's take a look at this function, y over x to the 4th, y to the 4th. We want to take a look at the limits as x, y go to 0, 0. So what might the limit be? For instance, if we plug in x equals 0 or y equals 0, and then make one of them equal to 0 and let the other one go to 0 and see what happens. What do you think the limit might be? It might be 0, but it's not. If you look at the xy plane, here you could set x equals 0 and let y go to 0. You can set y equal to 0 and then approach the origin this way. But let's approach along a different path, x equal y. F of x, where x is equal to y, we get x cubed times x over x to the 4th plus x to the 4th. So x to the 4th over 2x to the 4th is 1/2.